Okay, so that's quiz 1. Our next major assessment is exam 1, and you can look on the course schedule to see when that's going to be. I'll announce it as we get closer. Did everybody get my email about the formula sheets? So I gave you, it's a 4-page equation packet that you'll have access to during the exams, and I'll print that out. You don't need to print it, but if you want to begin to familiarize yourself with what's there and where on the page you can find it, you've got it now, and I'll post it on MU Online as well in case you lose that email. Has anybody taken a look at homework 3? All right, those are both 3 reservoir problems, I think. That's due on Tuesday. Submit it before class starts. Today we're going to talk about non-circular conduits and how we calculate energy losses when the pipe isn't circular. And then we're also going to revisit the idea of local losses, which we addressed briefly in fluid mechanics, but now it's starting to be a bigger issue since we're getting into hydraulic design. Any questions on the announcements before we start talking about non-circular conduits? Any questions at all? All right. So here are some images of 2 non-circular conduits. On the left are a couple of arch culverts, and there's no flow right now. This is a very arid area. This is a highway that runs between Dubai and a small rural town called Hatta out in the middle of the UAE. But they've got these enormous culverts, and how tall are they? I think they're about 12 feet tall. And the reason why is that when it rains in the UAE, it's raining onto rock and onto a desert that has very fine particles clogging the soil, so that most of the rain is going to wash down through the wadis, as they call them there. What we call a holler here, in the UAE they call it a wadi. And so when it rains, there's flash floods, just like we have here. We have flash floods because it's so steep in West Virginia. So they have to have a pretty big pipe so that the water can flow under that highway and so that it doesn't wash the road away. But when the water levels get high enough that it's just approaching overtopping, then that culvert structure will flow full, and it's non-circular. So we would need to have some sort of a method for us to calculate what are the head losses through a non-circular conduit. We can't use D because there isn't a diameter for a shape like this, nor is there a so-called diameter for a square pipe, which occasionally odd shapes occur. So we can't just directly substitute diameter, and instead what we can do is we can come up with an equivalent expression for diameter that involves the hydraulic radius. Now remember, what a hydraulic radius is it's the ratio of the area and the wetted perimeter. And wetted perimeter is any contact that the water is having with the conduit that carries the water. And so if it's a circular pipe, then the wetted perimeter is the circumference of that circular pipe. If it's open channel flow, though, remember we considered the case of trapezoidal geometry. Wetted perimeter for open channel flow does not include that top surface because the water isn't touching any sort of a friction surface. The wetted perimeter for open channel flow only includes where it's touching a solid. Okay, so we've got wetted perimeter, and that can give us hydraulic radius, and so we can modify the Darcy-Weisbach equation from the normal FLV squared divided by D2G. Instead of D, we use 4 times the hydraulic radius. And that's actually a substitution we can drop in any place. We would ordinarily use diameter. If the conduit's non-circular, we can adjust Reynolds number so that it's density, velocity, and where we'd normally have diameter, we can say 4 times the hydraulic radius divided by viscosity, or the way that I more often like to write Reynolds number. Normally we say V times diameter divided by kinematic viscosity, so we could say V times 4 hydraulic radius divided by kinematic viscosity. Relative roughness. Where do we use relative roughness? Relative roughness is where we're looking at either the K sub S or epsilon. You know, it's the equivalent sand roughness relative to diameter. And where do we utilize that? It's in the Moody diagram. Relative roughness is built into the Jane equation and the Colebrook equation. So relative roughness is just that equivalent sand roughness, epsilon or K sub s, instead of divided by diameter, it's divided by 4 times the hydraulic radius. So what that means is that for a non-circular conduit, then the Jane equation looks a little bit different as well. So here's what the Jane equation looks like. So F is 1.325, and where we'd normally have K sub s divided by 3.7d, what we have is K sub s divided by 3.7 times 4 times hydraulic radius. So that 4 times hydraulic radius is effectively in the denominator right next to the 3.7d. Here's our approximation for the Darcy-Weisbach equation, Reynolds number. So let's get some practice with that. I know you've been crunching numbers, so I'll do this one on the whiteboard and you can just follow along. We are going to find out water flowing through a concrete pipe where we've got an equivalent sand roughness of 1.6 millimeters. So this is a rough concrete surface. And the dimensions of that concrete box culvert are 1.2 meters by 1.2 meters. And the flow rate, 0.4 cubic meters per second. Okay, so we want to find out how much head loss is there through this structure. So we've got L equals 12 meters, K sub s equals 1.6 millimeters. Our cross-sectional area, 1.25 meters by 1.25 meters. So it's 1.5625 meters squared. And the flow rate is 0.4 cubic meters per second. All right. So I'm going to be doing this on the board, but I will bring up the solution so that whoever is watching at home stuck because they've got icy roads will be able to follow along. All right, well, let me continue on the board while the computer thinks about it. Our wetted perimeter for the shape of this box culvert, it's a 1.25 meters by 1.25 meters. So what's the wetted perimeter? Well, the water's in contact with all 4 surfaces, and so it's going to be 4 times 1.25. So the wetted perimeter is the 4 sides, each of which are 1.25 meters, and that means it's 5 meters in length all the way around. So the hydraulic radius then, R sub h, is the area divided by the wetted perimeter. All right. So that is 1.5625 meters squared for the area, divided by 5 meters of length for the wetted perimeter. So our hydraulic radius, 0.3125 meters. So what's the Reynolds number in this case? Density times velocity times 4 times the hydraulic radius divided by the viscosity. So this is water, typical conditions, 1,000 kilograms per cubic meter. The velocity of flow, if Q is 0.4 cubic meters per second, then V is Q divided by area. We calculated the area already. So the velocity is 0.256 meters per second. Okay, so I'll put in the 0.256 meters per second, and then we've got the 4 times the hydraulic radius. So 4 times 0.3125 meters. That's our numerator, and in the denominator, the viscosity of water, the standard conditions, 1 times 10 to the minus 3 Newton seconds per meter squared. So the Reynolds number for these flow conditions is 320,000. Now that we've got that Reynolds number, we can make the substitution into the Jane equation. I've run out of space on the whiteboard, so let me bring up the projector again and I'll show you the solution there. We used to have classes over in EL 101 in the lab building next door. It was perfect because the projector went onto a whiteboard and you could draw on the image, and we had tons of whiteboard space. Man, those were the days. You guys came just a couple years too late when we had this nice building that we don't like. All right. So we've got our Reynolds number and substituted into the Jane equation. Okay, so the Jane equation, remember, we've made this modification where instead of diameter on the left side, you know, in the denominator of the Jane equation, there's the two terms. There's the relative roughness term, and then there's the term that accounts for flow conditions with the Reynolds number. So here on the left, we have 4 times the hydraulic radius, and I had to convert my units. So here on the whiteboard, where I'd calculated that the hydraulic radius is 0.3125 meters, you'll notice that now on the screen, it's 312.5 millimeters. So it needs to be unitless, and I have my equivalent sand roughness in 1.6 millimeters. So either I have to convert the 1.6 millimeters into meters, and then I can use the hydraulic radius as I had calculated it, or I have to calculate the hydraulic radius to millimeters, which is what I did and which is what's on the screen there. And then the 5.74 divided by the Reynolds number to the 0.9 power. So putting all that into the calculator, the Jane equation returns that the F value is 0.0218. And then this is a pretty minor head loss. It's a short culvert. The water isn't flowing particularly fast. So there's not going to be a lot of pipe friction through this section. And so that may be good news, because if there's a lot of friction as the water flows through the pipe, then that can choke the flow upstream. So in this case, it may not be interfering with the flow like it otherwise would if there was a lot of friction. So we can express that head loss in terms of meters after calculating the Darcy-Weisbach equation. So I'll give you a minute to copy that answer. So non-circular conduits aren't that bad. It's kind of no big deal. You just have to make an easy adjustment and then move right along. The same method you already knew. Any questions about the example? Okay, well, let's revisit the idea of local losses, sometimes called minor losses, because compared to friction losses, the minor losses are usually lower in magnitude. When we write the energy equation, sometimes on the right-hand side of the energy equation we'll write H sub L instead of H sub F. And H sub L is more inclusive. H sub L means local losses and friction losses. Sometimes I get sloppy and just write H sub F on the right-hand side of the energy equation, and when I do that, what I mean is let's neglect these local losses. But for today, let's not neglect them. The way that we can calculate the local losses is by multiplying some k value that we look up from a table by the velocity head at a given location. So let's say that it's a bend. that's causing a localized reduction in energy. And the reason why it extracts some energy at this bend is that the flow is having to change direction, and that introduces turbulence. More turbulence than would ordinarily be present if the water is just flowing horizontally through the pipe without any special disturbance. But when we disturb the flow, we're taking energy out of it because there are some countercurrent swirling and there's eddies and a vortex forming maybe, and so the water isn't smoothly going through this transition. There's a lot of disruption to the particles as the water's flowing through that pipe, and so it's, in a sense, you're kind of choking down the effective flow area because you've got some sections where there's just a lot of disturbance and it's not really in those locations where there's countercurrent flow, it's not an effective flow location. And so we can sum up the effect of that turbulence by looking up a K value for the type of fitting we have and multiply it by the velocity at that spot. In the lab with the pipe rack, you remember that one of the local losses that you looked at was a pipe expansion. And in the case of expansions and contractions, what you can do is you can multiply a K value by the difference in the velocity head. There are some tables that would relate the energy loss to just one of those velocities. And so you have to be sensitive to the table that you're using and look at, is the K value calibrated to the difference in velocity, or is the K value that they've provided in this table related to an inlet or an outlet velocity. Last semester in the lab, the K values that I gave you were specific to an inlet or an outlet velocity. So just to summarize, a local loss is energy, instead of being distributed like a friction loss, a local loss is a result of localized flow conditions. And because of the reduced magnitude over the course of a pipe network, probably 90% of the losses are usually due to pipe friction, and less than 10% are typically due to fittings. So that's why we sometimes call those local losses minor. Pipe entrances, contractions, bends, fittings. We're going to look at some cases of each of those categories here. So this is a table from your book, and they illustrate the effect of contractions and expansions. And you'll notice that the angle of the contraction or the expansion affects the K value that you use. And so a 60-degree angle would indicate a relatively gradual taper between this diameter that's larger and the diameter that's smaller. And if you gradually taper, instead of having a sudden transition, 180 degrees means that it's not gradual at all. It's just big pipe, suddenly small pipe, with a horizontal face that's connecting them. And in that case, there's a lot more turbulence, and so the K value is bigger than the situation of a gradual transition. And then the bigger the difference in the diameters, the larger the K value as well. And so if your small diameter is only 90% the size of the big diameter, so that means almost the same size, then it's a relatively smaller local loss because the transition isn't as big. But if you have a big transition where that small pipe is only 20% the size of the original large diameter pipe, then you'd have a greater K value, so 0.08 versus 0.04. So I think you get a sense for the trends here. The table also has some valve types, globe valves, gate valves, and we've got some cross-sectional views of those different valve types that we'll take a look at. And you may remember, talked about in a pipe bend how the more gradual the transition, the lower the energy loss is, up to a point where the radius of curvature relative to the diameter of the pipe, the sweet spot seems to be a ratio of about 4. because that's the lowest K value. That's going to have the least amount of disturbance. But then when you go beyond that and you have an even more gradual transition, it's not that it's causing increased turbulence, it's just that the extra length, because you're making that transition so long, the extra length is introducing what's in effect a frictional loss, and that's why the K value begins to increase again. So the ratio of the radius of curvature to the diameter of the pipe is another thing that we can take into account when we're estimating the local losses. So here's some cross-sectional views of different types of gates. If you have a gate valve, it's essentially just a flat face that when it's a pipe that continues through, and if we interrupt the flow by putting in a plug, then there isn't a K value for that. If it's closed, then the K value is 100%. There's no flow through it. But if it's open and that gate's out of the way, then it's not causing much turbulence, because you'll notice this pipe is flat, and all we did was we removed a plug from a flat section of the pipe where it's not been interrupted. And so the K value is relatively small for a gate valve, but in a globe valve, the water's having to change direction 2 times before it actually gets through the globe valve, and besides changing direction twice, it's flowing through a tiny little hole inside the valve. I've got another cross-section that shows globe valve with a little bit better detail, but the point I want to make now is that for a globe valve, the K value is enormous, 10, compared to 0.15 for a gate valve. So you have to be sensitive to how much energy you can afford to lose when you're doing a hydraulic design. Now, the advantage of a globe valve is that it's less likely to leak than a gate valve. You can crank down a globe valve with quite a lot of force, and there's a rubber plug that can ensure that in a high-pressure environment there isn't going to be leakage, whereas a gate valve, water could seep around the edges of a gate valve more easily. A check valve is sometimes used in sewers, where you don't want to have backflow into someone's basement. And actually, that's a problem that they have more often than you'd think here in Huntington. During wet weather, there's a spot over by Ritter Park where it's between Ritter Park and campus. There's some homes that have basements that just every few years, before they installed these check valves, the sewage, because when it rains, we have combined sewers in a lot of Huntington, and so that means that both wastewater and stormwater is going into the same pipe. So on a rainy day, the pipe is full of rainwater and also sewage, and so then it would back up into people's basements, and of course that causes a lot of damage. It's costly to clean up, and the people don't like it. So a check valve is the way to have only one-way flow through a pipe. And these check valves, there's a variety of different types of check valves: a swing valve, a ball valve, where a ball is kind of like bouncing around inside of the valve, but then with the flow change direction, then that ball falls and plugs the flow so that the water can't go the opposite way. That's what these check valves do, is just kind of only allow the water to go in the direction that's intended. And a rotary valve is essentially a pipe segment that you rotate, and when it's open, then the pipe segment is connecting the inlet and the outlet, but then when you rotate, that pipe section isn't allowing any kind of flow through it. But the K value, you'd think it's maybe a lot like a gate valve, but the thing is that there's this center post in the middle of a lot of the rotary valves, and so the K value ends up being relatively high compared to a gate valve, although it's a lot more convenient to close a rotary valve because it's just a single quarter turn and it's open versus closed, whereas a gate valve can be a lot of turns to finally get the valve closed. These are some K values that are for the entrance of a pipe into a reservoir or a tank. And if it is just flush with the edges of the tank, then we would generally use a K value of 0.5. But if the pipe protrudes into the liquid, then the K value becomes 1.0. And so that just means that there's more energy loss as the water has to flow around this obstruction to get into the pipe, compared to just kind of, if you were going to draw streamlines of how does the water get into the pipe, the streamlines would be more gradual for a pipe that's flush to the edge, or if it's tapered, then it would be a lot more easy for the flow to transition into that pipe without turbulence, and therefore you'll notice the K value can be as low as 0.04, depending on the radius of the curvature. But a protruding pipe has more turbulence, and the streamlines don't converge quite as easily on that opening, and so they assign a K value of 1.0 in that case. And then this final figure makes the case that if you have an angled entrance into a reservoir, then that can introduce even more turbulence than if it is at a 90-degree angle. And so you'd have the same 0.5 plus some additional local losses depending on how dramatic that angle is. Okay, I like this illustration of a globe valve because it kind of gives you a better sense of the path that water particles are taking to get through it. The water enters the inlet side of the valve, and it has to go down before it takes a sharp turn upward, and it's going around this plug, and the diameter of that plug is quite a lot smaller. The effective diameter of where the water can squeeze through is going to be less than the opening of the hole, and that's why we'd see a K value of 10 for a globe valve, is because it's changing directions a couple times, and the opening inside the valve is relatively small compared to the opening on the inlet and the outlet. Whereas a ball valve can just have a quarter turn, and so it's really convenient. The water flows through there, but they often will have a center post going through the center, kind of just to maintain the structural rigidity of that ball. Okay, so let's get some practice revisiting the idea of local losses. We've got 15 minutes, which will be plenty for this example. Let's take a look. We've got a pipeline. Water's flowing through it. It's 350 millimeters, and we're going to use the Hazen-Williams equation to tell us the pressure downstream. So this is Hazen-Williams plus energy equation. And in the energy equation, we're going to account for both the local losses and the friction losses. Hazen-Williams we'll use to account for the friction losses. Local losses, we have to add up the three K values. Okay, so we've got a single bend where we've got a K value of 0.25, a globe valve that even when it's open has a K value of 10, and then another bend where the K value is 0.15. You can add up the Ks as long as, now this is an important point, let me emphasize, you can only add them up if the velocity is the same at all 3 points. And we have one pipeline of a diameter that isn't changing. The diameter is 350, so the velocity at those three locations will be the same. But if we had a variety of different diameters, then you'd need to find the velocity at each location where there's a local loss and use that velocity head for that diameter. In this case, we can aggregate all three together. All right, so I'm going to pause for now. I'll circulate around to address any questions you might have. Of course, feel free to discuss this one with your classmates, and then we'll take a look after a few minutes at the solution on the screen. All right, so we summarize all of the givens to begin with, and there's two things that are going to be taking pressure out of the system, the local losses and the friction losses, and then of course there's going to be a pressure differential just because there's an elevation difference between the 2 points as well. So the energy equation will handle the elevation for us, but we need to calculate the local losses and the friction losses. Okay, so the Hazen-Williams is our estimate of friction losses, and it's 43.1 meters there. And then the local losses are estimated at about 8.5 meters of these local losses. And then let's take a look at the energy equation. Here's the full version of the energy equation. well, not the full version, because I guess if we were really going nuts, then we would have the kinetic energy correction factor, remember alpha, and there's no turbine though, so I canceled out the turbine on the left-hand side. There's no pump, so I canceled that out as well. The water velocity is constant in the pipe. Now I've got some good questions over the last few days from students asking, when do you cancel out the velocity head at 2? And I think it was related to that problem where a water pipe is going into a building. And so, if the water pipe is going into the building and then it stops, so if we have static conditions at a certain location downstream, then you'd cancel out the velocity head at that location. In this case, it's water that's continuing to flow through the pipe at both A and B. So what we say is that the velocity at A and the velocity at B are equal, and so therefore they're going to just drop out of the energy equation. So I rewrite it in terms of the pressure at 2, just rearrange things algebraically. And so we've got the pressure head at 1, and I just like to do things in more steps than is necessary so I can see if I've made a mistake and to get a sense of where is the energy and what's taking it out. That's why I do these intermediate steps, is it's good for preventing errors, but also it tells you that at location A, you've got 66.25 meters of head. That's kind of like how much energy there is to work with. That's the starting point. And all these other factors are taking energy away. And so you can get a relative sense that it's the difference in elevation is taking out 12.5 meters of head of the 66.26 that we had to begin with. And then the friction losses is taking out 43, the local loss is taking out 8.5, and so on. And so I think it's not necessary. You can arrive at the correct answer without writing out these extra steps on the page, but it's useful for a variety of reasons, and I'd encourage you to, graphite for a mechanical pencil is cheap. So just go ahead and write a little extra so that you can check your work and elaborate on the solution. We get in the end that it's 21.3 kilopascals at that downstream location. All right, so that's all for today. Let's look at these announcements one last time. Your homework assignment's due on Tuesday. I'd encourage you to get an early start on that. In case you have questions, then you can ask me sooner rather than later. Feel free to stop by during my office hours or send me an email, and I'll try and check it a couple times through the weekend, and I'll do my best to respond if you've got a question. So that's it for today, and I'll see you next week.